Hello YouTube! Today we're going to be talking about 1D projectile motion. This one's going to be less about learning stuff and more about just having an excuse to practice more on the kinematic equations. This is sort of the most common situation in which you'll have acceleration with constant acceleration as your sort of way that the object is moving. And so this tends to be a good way to practice it. So more about practice, again, than it is about learning specific new things. So diving on in. Ideally, end of the day, you're good to go modeling 1D projectile motion. In particular, if you can do out the definitions, know when something's a projectile, and then find the hidden givens for any problem based on a description of the situation, you should be in good shape. So what is a projectile? Well, anything that's only being accelerated by gravity is called in free fall. So pretty much if you drop something, if you throw something, if something rolls off of a table, anything like that is going to be a projectile as soon as it's in the air. Now, for the beginning, we'll be ignoring air resistance. We will eventually have to not ignore air resistance, and at that point, they won't be projectiles anymore, or at least they won't be in free fall. Anything that's in free fall is called a projectile. It's also a projectile if it's experiencing just air resistance. But for our purposes at the beginning, we're, again, ignoring that. And the reason this is particularly interesting is because everything on the surface near the surface of the Earth accelerates at the same rate as each other, meaning that no matter how heavy it is, no matter how light it is, it should accelerate at the same rate. It'll change its velocity by the same amount every second. The reason why this might be a little counterintuitive, and we'll learn more about this later, but the reason why this tends to be a bit counterintuitive is because air resistance actually gets bigger or has a larger effect on the object the lighter the object is. So if you have no air, this will 100% be true. If you have air, gravity is still trying to accelerate everything at the same rate. It's just that some of that might be canceled out by air resistance, and more of that will be canceled out if the object is lighter. So light objects will accelerate less, making this not necessarily people's first intuition. But again, in the absence of air resistance, everything accelerates at the same rate. And that rate is pretty much 10 meters per second squared down. The actual number is not as neat as that, but it rounds pretty closely with less than 2% error to 10. So we tend to just use 10 to make the numbers easier. Although I believe the textbook that we're using for the in-person version of this class does use 9.8 for the answers. So just if you're slightly off, assume that's why. If you see the word dropped, what that's going to mean is that your initial velocity for the problem is going to be 0, because it's starting from rest, then you let go, then it starts moving. When you see lands don't set that velocity equal to 0, they're asking you to figure out how fast it'll be going when it's hitting the ground. If an object is at its maximum height, what's happening is the object is getting to the top, it's stopping and turning around. So if you think about its sort of velocity graph will start out being positive, and then it'll decrease as it slows down on the way up. Then it'll hit 0, that'll be at the top when it turns around, and then it'll be going negative, meaning that the object is going down and speeding up. At any given height, another thing that's interesting about this, and this is something that actually one of the worksheets asks you to prove, at any given height, the velocity of the object will be the same but negative when you're going down versus going up. And a way to sort of conceptually prove this is that when you're watching something go up then down again, it actually winds up being such that you can't tell if the video, if you're watching a video, if it's being played forward or backwards, because the process of the motion is completely symmetric. Great. Let's just do a couple examples and then call it. First one should hopefully be pretty straightforward. Just we have an object. It's being thrown into the air with an initial velocity of 30 meters per second. How high in the air is it going to go? So, this is 1.7, 1D projectiles. Great. So we've got our objects. we know that the initial velocity, and I'm actually going to say Vy naught because this is happening in the y direction, is plus 30 meters per second to show that it's going up initially. We're being asked for the displacement to get up to the top. Well, we know that we're reaching the top. Specifically, it's the top because it turns around, so this tells us that our velocity at the top, which is our final velocity for this one in the y direction, is going to be equal to 0. We also know that our acceleration in the y direction, because it's gravity, is going to be 10 meters per second squared down. Because I had my initial velocity be positive while going up, my acceleration should be negative. So those are our givens. At this point, we just have to find a kinematics equation. We have acceleration, we have velocity, and we have displacement. So if we want to do it in one step, it should be final velocity squared is equal to initial velocity squared plus 2a delta y. Taking a double check, we have this one, it's 0. We have this one, it's 30. We have this one, it's minus 10. So our only variable is delta y. Going ahead and plugging in the 0, just to make our algebra a little easier. All we got to do is subtract off Vy naught squared minus Vy naught squared. That gives us negative Vy naught squared equals 2ay delta y. We're looking for delta y, so just divide each side by 2ay. Divide each side by 2ay. And we'll get negative Vy naught squared divided by 2ay equals delta y. Spending just half a second going through how I knew that this was the equation to use, looking at all of our available kinematics equations, and you could rederive these in theory, but it's nice to just sort of have them in your back pocket. We've got Vy equals Vy naught plus ay times t. The problem with this one is we're not really asked about the time at all. So you could use this, you could figure out the time and then use that with another equation to figure out the distance, but that's kind of extra work off of just using this one equation. If we look at the second one, this does have delta y in it, the thing that we're looking for, but the problem is if we want to go straight to using it, it involves time. And so that's not really going to work unless we go through a second step, this one, to figure out what our time is. Alternately, we could use that our displacement is equal to Vy plus Vy naught over 2, and that looks promising, but again, time shows up and kind of ruins it. So this is the equation for the kinematics that has the variables we're actually given, and also includes the variable we're looking for. So yes, we have to do some algebra, but this lets us do it with one equation. Plugging in our numbers, we've got negative 30 squared divided by 2 times negative 10. It gives us 300 over 20, which is 45. So 45 meters up. Great. Next problem. This next one is going to start out a lot tougher, or at least a little tougher. Have some more stuff we have to think about it, but then it'll eventually basically turn into the exact same problem as the last one. So we'll probably wind up using the same solved form. But to start with, it's going to be a little more tricky and involve a little more thinking. So for this one, our situation is that we've got this window, and we know that the height of the window is 1 meter. And we also know that to get from here to here, the time for this is equal to 0.1 seconds. And we know that our acceleration is equal to negative 10 meters per second squared. Now we're asked what the height from here to here where we get to the top is. And I'm actually going to change the way that I'm writing this. And I think we're good to, that's our givens, we're good to swap over. Because for me, this sort of has 3 different locations. There's the bottom, which I'll call V1. There's the middle, which I'll call V2. And then there's the top, which I'll call V3. Now I don't know anything about V1 or 2. But I do know that the velocity at the top needs to be 0. I'm asked for the displacement from location 2 to 3. If I want to find this, I'm going to need 3 of the variables from the kinematic equations. The problem is I only have 2. I have my acceleration. It's still negative 10 meters per second squared. And I have my final velocity, but I don't have my time. And I don't have my initial velocity. So I need a way to get one of those 2 things. Well, my initial velocity for this section, from here to here above the window, is the same as my final velocity while in the window. So what I can do is if I look at the window section, for this section, I have my displacement, I have my time, I have my acceleration, and I have my velocity. And I'm missing my 2 velocities. So I can use an equation to figure out what my initial velocity was, my final velocity is going to be, which we're actually going to have to use 2 equations for unless we want to be kind of tricky conceptually and think about it on the way down instead of the way up. But that's kind of a little more work than we, like mental legwork than we need to do. So we'll use 2 equations to get our final velocity. Once we've got our final velocity at the window section, that becomes our initial velocity for the next section. And we can use that with one of our equations to get the delta y. And that'll be the same as this process because we'll have the same set of givens. We'll know our acceleration, we'll know that our final velocity is 0, we'll know our initial velocity, and we'll want to figure out delta y. So, doing that out. For our first section, I don't know my final velocity, so I'm going to want to use an equation that doesn't have my final velocity. My displacement from the bottom of the window to the top of the window is going to equal 1/2 times my acceleration times my time squared plus my initial velocity times time. I know everything except for initial velocity, so I am good to just subtract stuff off and solve that way. We've got minus ayt squared minus 1/2 ayt squared. That gives us delta y12 minus 1/2 ayt squared equals v1t. Divide each side by v1. Divide each side by v1. That's what we're looking for. Divide each side by t. I'm so used to solving for time. Divide each side by t. And we get v1 equals delta y12 minus 1/2 ayt squared divided by t. Throw our numbers at it, and we'll get 1 minus 1/2 times 10 times 0.1 squared, all divided by 0.1. 10 times 0.1 squared is going to be, 0.01, so 0.1. So 1/2 times 0.1. 1 minus 1/2 times 0.1 is going to give us 0.95. 0.95 divided by 0.1 is going to give us 9.5 meters per second. So we've got 9.5 meters per second as our final velocity after that distance. Sorry, our initial velocity at the beginning. Yeah, that'll work. This is our V1. Now we're looking for V2. Well, thankfully, the equation to get V2 is actually pretty straightforward. You could use anything with V2, but if we look at this one, it actually comes pre-solved. So all I have to do is plug in 9.5 plus minus 10 times 0.1. And that'll give us 9.5 minus 0.1, which gives us 9.4. From here, I'm a very yawny fellow. Sorry, so there's our final velocity for V2. At this point, our givens are actually the same as this one, so I'm going to recycle our algebra. We can say that our displacement from the top, from the top of the window all the way up to the top of the above window section is going to be equal to negative v2, our initial velocity for that section squared, divided by 2 times our acceleration. So that'll give us 9.4 squared, negative, divided by 2 times negative 10. Which my calculator says is 0.42 meters. Seems a little low. Oh, I did a 9 instead of a parenthesis. That would be why it's a little low. 4.4 meters. I feel like I did something wrong. One sec. This should be negative. This should be plus. This is 1.05. This is 10.5. This then becomes 10.5 plus 0.1. This is 10.6. This should be 10.04. Sorry, 10.4. This should be 10.4. This should be 10.4. And we should get 5.4 meters as our final answer. Hopefully I didn't make any other algebra guffaws, but the concepts of this one and the process of, again, saying, okay, well, there's sort of 3 things happening, breaking those 3 sections up and connecting them via the final velocity of one section being the initial velocity of the other is a fairly common strategy that happens a decent chunk of the time. That's it. So thanks, YouTube. Goodbye, and let me know in the comments if you have any questions. Hope you have a great day.